So we've sampled some puzzles. I attempted to vibe code a solver. It didn't work very well. In 6 months, it'll probably work better with a different model and a slightly different prompt. It might have worked the first time. Even so, it's a bit of a crapshoot. But the truth is, I already know how to do this. What I would typically do is take one of my existing solvers and tweak it a bit for this particular puzzle. Much faster than writing it from scratch. But there is a trick, a tool actually, that I consistently use when writing quick brute force solvers. And that tool is OR Tools, a solving library from a small team at Google Research. I've been using it for years. OR Tools is designed to solve constraint problems, and as it happens, pretty much all the puzzles I make are constraint problems. Sudoku is a classic constraint problem, and pretty much every off-the-shelf constraint solver I've used provides an example of using it to solve Sudoku. Sudoku is kind of the hello world of constraint solvers. In addition to OR Tools, I've tried several other constraint solvers as well over the years. For my uses, I found Google OR Tools to be the best one. Why? Well, here's 4 reasons. It's quite fast. It's well supported and mature, at least 15 years old and still being maintained. It's easy to install, and I don't think it's going anywhere soon. That can be a problem when you rely on third-party tools. There was another constraint solver I liked a lot called Numberjack. It has a fairly elegant API, but it's buggy, and it hasn't been updated in quite a while. OR Tools has a Git repo, and in that repo are some examples in Python. In the Python code is a Sudoku example, of course, and that makes a good starting point for understanding how to use it. I'm also going to mention Håkan Kjellerstrand. Håkan is a Swedish independent researcher who has kicked the tires on more constraint solvers than just about anybody. He's posted a huge variety of puzzle examples for a wide variety of constraint solvers, including OR Tools, on his GitHub, shown here. His collection of OR Tools examples is significantly larger than the one in the OR Tools repo, and it includes tons of puzzles. If you're looking to solve a well-known puzzle like minesweeper or nonograms, there's a good chance you'll find it here. I've made my own Sudoku example for OR Tools. It's not quite as elegant as the one supplied by Google, but it may be a little easier to understand than the OR Tools example. Let's take a look at it. In OR Tools, you have a model and a solver. You start by setting up the model. The model keeps track of a series of variables, often booleans or integers. The underlying SAT solver in OR Tools, like most SAT solvers, works with booleans. But OR Tools takes care of some stuff under the hood, so you can also work with integers, which is convenient for many puzzles. Now, you may find that if you find a way to represent your puzzle using just booleans, the solver runs faster. Anyway, for Sudoku, it's convenient to allocate a set of integer variables, which are going to represent the squares of the puzzle. Each variable has a value from 1 to 9. After we set up the variables in the board, we can begin to define the rules or constraints of the puzzle. The 2 functions used most commonly for this are add, which can be used to set up all kinds of arithmetic constraints, and add all different, which is a shortcut which allows you to specify that each cell is different. We'll use the add all different constraint to set up the basic rules of the puzzle, each time passing the list of cells in the container. In Sudoku, every row has a set of unique or all different digits, same with every column, and finally the same with every 3x3 block. After we've set up the constraints, we go through the puzzle itself and set up the givens or clues. For each given in the puzzle, we use add to create the constraint that the particular square be equal to the given value. So we're adding the constraint that there's a 5 in this square and a 3 in that square. There's something a little unusual or counterintuitive about how the equality operator and other comparison operators work with model variables. The result doesn't get evaluated right away like it normally would in a Python script. Instead, OR tools overrides the comparison operators and returns a constraint function rather than a literal result. The constraint is what is being passed to the add function to be evaluated later during the solve process. You can use the add function to say that a cell is equal to a value or another cell, or greater than or less than a value or a cell, or that the sum or product of a collection of cells has some property. Very useful for killer Sudoku or Ken-Ken. Now we're done setting up the constraints and we can solve the puzzle. The solver will find the first solution that meets the constraints and return. You can then inspect the state of the model variables to see what the solution is. After calling solve, we can use the return code to see if it succeeded. If it returns either optimal or feasible, that means the solution was found. In practice, when a puzzle is solvable, you usually get optimal for the return code, but I guess there are some types of more ambiguous problems where it uses feasible. Infeasible, the first thing I'm checking for here, means the puzzle can't be solved by the solver. It basically means it's an invalid puzzle. Now I should point out that in this particular example for Sudoku, I am not checking if the puzzle has multiple answers. It just returns the first answer it finds. If you're just solving puzzles that you already know have a single solution, that's fine. But for our purposes, for puzzle construction, we actually need to know if there are multiple solutions, because we'll be using this solver on candidate puzzles, which don't necessarily have single solutions. That'll be a frequent occurrence, in fact, as we do clue reduction, as you'll see shortly. We want to use the solve process to ensure that there is a unique solution, and that requires a little extra code. There's a few ways to do it, and I'll cover that in a moment. For a non-Sudoku puzzle like Minesweeper Sudoku, we already saw that, today at least, in early August 2025, it's still hard, or at least unreliable, without precise prompting, to vibe code a brute force solving function. Maybe in late August it will be easier. I got a lot closer to success using a more precise prompt based on my own methods. I tried asking Claude to make a solver that uses OR tools. Here's my prompt, which contains this more precise language. I said, in part, I want to make a new minesweeper solver that uses the SAT solver and OR tools. This will go here. It will contain a solve function that accepts a puzzle string and returns either a solved puzzle string, multiple solutions, or no solution, ... The solver function will use OR tools. It will set up a one-dimensional array of vars, which are 0 or 1, indicating the presence of a mine. We will set up constraints so that the rows, columns, and 3x3 containers each have 3 mines, and the clues in the puzzle indicate the sum of adjacent mines. In the first attempt, Claude got very close enough that I was able to patch it and get it working pretty quickly. I should mention that it completely ignored my request to use a one-dimensional array of vars, and this is because while I prefer this style, the vast majority of OR tools Sudoku examples out there tend to use either dictionaries or two-dimensional arrays to represent the board. I just happen to like one-dimensional arrays for that because it resembles the way I store the puzzles in my text files. Also, Claude included some vestigial code it didn't ultimately use elsewhere. Still, the first version Claude made was mostly correct. It set up correct constraints so that each row, column, and 3x3 block would contain 3 mines. That's great. It set up the clues properly so that the count of adjacent mines would be equal to the clues number. That's also great. But there were 2 significant bugs that prevented it from working. The first has to do with an implicit rule of these puzzles and minesweeper boards in general. The presence of a number on the board indicates that the specified numbered square does not, in fact, contain a mine. You can't have a square with a number on it that is also a mine. This is usually not stated explicitly in the written rules for this puzzle. It's assumed. But we can't assume it when we set up the solver, or it'll place mines in those squares, and you'll end up with alternate solutions. This is a common problem I've encountered when coding puzzles for constraint solvers. There are often 1 or 2 implicit rules you have to add, or the solver does dumb things like putting mines on numbered squares. This is the kind of bug I probably would have made myself when initially coding the constraints for this puzzle. It was easily found when the solver came up with bogus solutions. The second bug had to do with the method it chose to identify puzzles with multiple solutions. It had a cool idea, which is that after getting the first solution, it would add an additional constraint to the model. The constraint that the answer couldn't be the answer we just found, the first solution. And then it would call the solve function a second time. The model, now having this new constraint, would then find any other solutions. If it then fails to solve the puzzle has a unique solution. Otherwise, it has at least two, and we can mark it as a mult. This is a cool idea, and it almost worked, but the way it tried to add the constraint for that condition was bugged. These two problems were easily fixed, and after fixing them, the solver worked great. So I used it as the basis for the OR Tools minesweeper solver that is currently in my minesweeper repo. I did end up rewriting it a bit. The method I just talked about of calling the solve function twice for each puzzle to check for duplicate answers is clever, but it's not very efficient. If we could just call the solve function once and have it iterate through the first two answers internally, it would be faster. There is a way to do that, and I tried it both ways, and the rewritten version was twice as fast. The basic idea is to use a single solve and have it continue looking for answers, saving them into a list, and then exit the solver early once you hit a second answer. OR Tools supports this methodology using callback functions. You set up a class that inherits from a built-in class called CP-Solver Solution Callback. You set one of these up, and it receives the onSolution callback call each time the solver hits upon a solution. Inside that function, you can save the different solutions encountered and return early if you hit two. You're wasting your time otherwise. In order for callbacks to work, you have to turn on the enumerate all solutions flag, and you have to pass the callback object as a second parameter to the solver after the model. After the solver returns, you can then query the callback object to see if there are 0, 1, or 2 solutions. The script solvepuzzles.py uses this solver on the test suite we made in the last video, and it successfully solves all 13 puzzles, which I am pleased to report I managed to transcribe with no mistakes. Who knew? I've added an additional puzzle to the test suite, which is all dots. That blank puzzle tests that the solver is correctly identifying puzzles with more than one solution. Also notice that if you seed the solver's random number generator with different values, you can make it generate random solutions to the blank puzzle. That's a very useful feature, being able to generate different random answers. It is, in fact, the first step to making a generator. So now that we have our working solver, we've done the hard part, and we can easily make a generator. The basic plan is this. We'll generate a candidate answer. You can use OR Tools for this by seeding its random number generator and solving a puzzle that has no clues. This will produce a different random answer each time it's called. Alternately, we can probably vibe code an answer generator pretty easily. That'll probably work, but since we already have an OR tool solver working, we may as well make use of it. We then can use that answer to make a super easy candidate puzzle by cluing every single square of the puzzle that can receive a clue. This produces a grid like this, where the answer is super obvious. Then we'll refine the puzzle by removing clues in a random order, one at a time. Each time we remove a clue, we'll test solve the puzzle, and if it can't be solved, we'll keep that particular clue because it's necessary. If it still can be solved, the clue is redundant and we can remove it. Typically, when the puzzle fails to solve, it means we've gone from having a single solution to multiple solutions. And that's why it's important to be able to detect multiple solutions. I don't think it can go from 1 to 0 solutions by doing clue removal. Or if it does, there's probably a bug in your code. This clue removal pass makes the generator take a long time, since it has to call the solver a lot. I typically do 3 or 5 attempts at clue removal, starting from the fully clued puzzle each time and using different scrambled orders. Each pass makes a different puzzle, and I choose the one with the fewest clues. This makes the constructor take even longer. There are some tricks for speeding it up. Sometimes you can remove a big chunk of random clues, like half of them, before you need to start calling the solver, which gives you about a 2x speed up. After we've removed the clues, the generator is done. We've made a puzzle. And to remind you, we're not done yet. We'll use this first generator to make a big test suite. And then we'll use that to improve our solver so we can properly grade the puzzles. These remaining steps are simple enough that we can use Claude to help implement them and write most of the generator. I'll do it bit by bit rather than attempting to one-shot it. Here we go. Okay, here we go. It reads my solver. It's creating the script. And there's the script. Let's take a look at it. Lots of comments. That's a much better method of generating a long string of dots. Like it. Good call. This looks good. It's generating the fully clued puzzle. It's generating the puzzles and it's printing the puzzles. I love it. Let's see if it can run it. And we don't need it to keep doing stuff now. It's working great. Okay, so it's obviously generating extremely fully clued puzzles, so then we just need to add the refine. Okay, my wording isn't great, but let's see if it can work with it. Okay, yeah, so it's doing 3 passes. It's starting with, it's shuffling the positions. It's calling solve. Okay, and let's, okay. Let's let it run. Actually, I'm going to run it myself. It is definitely slower, but it's working. And now it's generating puzzles with fewer clues. I want to get a better idea of how fast it is. So let's add some timing. Some elapsed time measurement and report it. Okay. Accept. All right. Okay, and I'm going to stick a comment in front of the time report. There we go. Do it again. Okay, so it's generating 10 puzzles in about 4 seconds. So, okay, not bad. All right, we've got a puzzle generator. I'm going to use it to generate a test suite, and I'll stick all this in the repo. In the next video, I'll show you how to print the puzzles to PDF files, SVGs, and PNG files. And then in the video after that, we'll rewrite the solver so that we can start grading the puzzles for difficulty. See you then.